Hi folks, it's Mr. M here with another video. This time we are looking at lesson number 12 in our series of MCR3U. And we are looking at a review of quadratic functions. So this is something that we would have or should have learned in grade 10, but we're just trying to see all the essential concepts pretty much in a nutshell. We're just trying to investigate and remember the three forms of quadratic functions, or like the three forms of a quadratic, right? So we got right here, number one, vertex form. This is probably, in my opinion, the most useful form out of all of them. Not that the others are bad, but this is probably by far the easiest to graph, the easiest to extract key information from. So vertex form always looks like this. So in function notation, if we have a function g of x, the output, right, can get horizontally translated, and it's squared, and then it's shifted vertically by some constant there, and then I translate it up or down. So it generally, like, this is an example, but the form of a like vertex form looks like this. So I'll just say like f of x is equal to a times x minus h squared plus k. So that is the general equation for vertex form. Okay, and what's important from this is I can now say, deduce, let's say this example right here. So the direction of opening is going to be down whenever a value is negative. Okay, so down, the reason is because a is negative. That's my short form for negative, right? The vertex, what's really nice is vertex form. I can extract the vertex. It's just going to be h comma k, which is equal to -1 comma -10. You just got to be careful because in vertex form, right, it's negative h, which is telling us from the equation, whatever number this is, I got to negate that. So that's why the h value is -1. Okay. The axis of symmetry, we give that the shorthand AOS, right? This is just the x value of my vertex. So axis of symmetry is literally x equals -1. So if I were to, like, sketch this rough sketch here, I know my vertex is now -1, right? -10 down here. That's like the starting point of my quadratic, really. And then it's opening down, so I know it's going to look something like this. Now, this axis of symmetry is literally the line that cuts that quadratic in half. So that's x equals -1. In other words, the x value of my vertex, right? Now, if the x value of my vertex is my axis of symmetry, the y value of my vertex is what we call my optimum value. Optimum value. In other words, it's my max or min. It really depends on the direction of opening of my parabola. If it's opening down like this, it's going to be a maximum. But if I had another parabola opening up, then that would be the minimum, right? So in this case, the optimum value is just the y value of my vertex. So it would just be, in this case, it's literally a maximum. You could see, right? It's opening down, and I would just say that is equal to -10, right? As you know, I could say the maximum is y equals -10. All right, so it's just that line right there. Okay, good, horizontal line there. So cool. Now I know max. I know the key features of like the parabola. Sorry, took a pause there. But yeah, so when the optimum value occurs, so I guess here it's just wanting us to circle the fact that it's a max. Here it's literally asking the same question: when does the optimal value occur? Well, it happens at -10, and this is literally, like I said, the y value of vertex. Okay, so that's so I should be a little bit clear. Okay, so here's what I was pausing there for a second, and I should be clear. When I ask for a value, I don't want you to give me an equation. You can literally just say it is -10. But if I ask you for an axis right? That's an equation. So that's why I give x is equal to negative 10. So strictly speaking, from optimum value, you can literally just say negative 10 because it's just that value, the y value, right? But for axis of symmetry, since it's an axis, it's like an equation. Well, now you kind of have to tell me, all right, what is that equation? It's always going to be x is equal to something because it's that x equals something y. Okay, so just a little bit of a side note there, just to clear that up. The y-intercept, well, from here, to find any y-intercept from any equation, the key is to set x equal to 0, right? That the line that the y-axis is literally x, in other words, known as x equals 0 because it passes through the x-axis at 0. And I just set this to my function right here, and then let's solve this and find out what the y is. So g of 0 is equal to negative 1/2, and I get 0 plus 1 squared minus 10. And so this is going to be negative 1/2, 1 squared minus 10. This is going to be just negative 1/2 minus 10, which will just be negative 10 and a half. Yeah, that's fine. So the y-intercept, my answer would just be, well, it's an intercept. It's kind of like a point, right? That point right there. It would be x is equal to 0 and y is equal to negative 10 and a half or 10.5. Anyway is fine. I'll write 10.5. Sure, negative 10.5. All right, cool. So now I know that as well. And by the way, just to make it clear again, you could write this in any way you like. You could write it as a mixed fraction. You could write this as an improper fraction. 2 times 10 plus 1 is 21, right? Because this whole thing, that's like a bracket right there. Then I deal with the negative afterwards. So negative, and then 21 over 2 would be the same thing, or I could just do negative 10.5. Just a side note on fractions there. These are all equivalent, right? Same thing. Cool. So now I know how to get the y-intercept. Last thing here is the range. So range is like similar to what we talked about before in domain and range. I'm looking at, well, what is the scope of the y values of this function. So it's literally everything lower or equal to my optimal value because it's going down. So I would say y is an element of the real numbers because it's a function, right? It's continuous such that y is less than or equal to negative 10, right? That is my range, and that would be everything. Okay, all right. So that's vertex form. A lot of information, a lot of things to gather from there. Next on the list, we have standard form. So this is like the default form. It's probably not the most helpful, but it is where like standardized. It is generally the default form that we're given functions in. So the way that this looks, standard form, for a quadratic, right? These are functions with exponents like degree 2. Exponent, the largest exponent in the polynomial is a 2. And so the format of this function is going to be f of x is equal to ax squared plus bx plus c. So that's what standard form looks like. And if it looks like this, so here we have an example. So I'll just highlight this for you. Here we got an example. And let's take a look at the direction of opening. So whenever the direction of opening is negative, like that a value right there, it's going to be down, right? And the reason for that is a is less than 0. It's negative. A, by the way, cannot be 0, equal to 0, because if it was, it would not be a quadratic, right? 0 times x squared would disappear, and I'd get something that's linear if a was. So a has to be either less than 0 or greater than 0 for it to be a quadratic. All right, so now we know that it's opening down. That's good. You don't, you could just say down, that's fine. The y-intercept, well, the thing of value that I can get from the standard form is literally the y-intercept, because when I plug in x equals 0, these things will always cancel. The ax squared plus bx will cancel, disappear because it's just 0, and I'll end up with this constant right here. So that constant in standard form is always my y-intercept. So it's just going to be 0, 11. So that's the beauty of standard form, is I get the y-intercept immediately. And that's about it from that. Okay, so nothing else there. Next, we get into this last third and final form for a quadratic, which is factored form. So factored form is generally more helpful than standard form. Here's an example that we have, but this is the format of factored form. So it looks like this. F of x is equal to a x minus r x minus s. Okay, so that is the general format. Notice that the coefficients of x have to be 1. So whatever, I need to factor out whatever numbers in front of x to make, and combine it with a to make sure that the factors, the coefficients in front of x are 1. And then r and s here are what are called my, my roots or my zeros of my function, right? When it crosses the x-intercept. So that's what factored form gives me. All right, so here, again, direction of opening. This is positive, so I just say up, check. Okay, so this is where it gets interesting. Factored form, if I were to draw a sketch of this function that I have here, literally the zeros are just literally what value of x makes that 0. So I would see it would be like literally x equals 4, right? What value of x makes this 0? It's just -2. So those are my zeros, right? You're essentially just solving the linear equation x plus 2 equals 0. Because when I'm finding my roots, right, I'm setting y equals 0, x-intercepts, right? Y is equal to 0, and then it's just like the 0 property rule. I'm looking at, well, this has to be 0 or this has to be 0 in order for them to multiply. 3 can't be 0 and to get 0, right? Just something from grade 10 that we learned. So that's how we find the x-intercepts or the roots. Roots, by the way, same thing as x-intercepts for short. And so, yes, so I have my two x-intercepts, which I just found here. It's going to be 4, 0, and -2, 0. All right, my two x-intercepts, nice. So what does this look like? Like on a graph, literally on a sketch, there'd be an x-intercept at -2 and another one at 4. And I just connect them, and I know it's opening up because a is positive, something like that. Okay? All right, good. Next thing is axis of symmetry. Okay, so if I have factored form, the way that I find axis of symmetry is I take my two x-intercepts and I find the middle of that. So finding the middle is like finding the average. I would just say AOS is equal to, so the way I find AOS, x, it's an equation, x equal to something. Like down here, trying to find x equal to what? I'm going to add the two x values here, the x-intercepts. So 4 plus -2, and then divide that by 2. Find the middle of that. So that would be 4 minus 2, which is 2 divided by 2, which is equal to 1. So my axis of symmetry is just x equals 1, which is that line down the middle. Okay, now when I want to find the max min, well, first of all, is it max or min? Well, I could see clearly that it's minimum, so I'll just circle here minimum. And then when it's like, when does the optimal value occur? All I'm going to do here is just plug in my axis of symmetry, x equals 1, and I'll replace x with 1 and figure out what my y value is. That'll give me the optimal value, right? So I'll just say, well, y is equal to 3 times the x that I got here was 1. So 1 minus 4 times 1 plus 2. All right, and if I simplify that, that's going to be 3 times -3 times 3, lots of 3's there. So that's going to be -27. Okay, so that is the optimal value. Okay, just a side note there. So this value right there, the y value of that vertex is -27. Okay, so really cool. Now, essentially, I know the vertex, right? Everything leads itself to the next. So the vertex is the combination of axis symmetry, which is 1, and the minimum, or the minimum value in this case, so -27, the optimal value, right? Nice. So that's how I got the vertex. Next on the list is y-intercept. Well, for y-intercept, I set x equals to 0. So I'm literally going to it's generally a good idea to start with the function, like instead of like expanding or whatever, but just use that. whatever you're given, right? So y is equal to 3. Y-intercept means x equals 0, right? X, by the way, roots here, x-intercepts means y equals 0. And it's just using the 0 property, right? That's how I figured those out. But here, for the y-intercept, I'm setting x equals 0, so this is going to be 0 minus 4, 0 plus 2. But this would just be 3 times negative 4 times 2, which would be negative 12 times 2 is negative 24. So I just found my y, so the y value would be negative 24, so the y-intercept would be 0 in the x and negative 24. Okay, so that is the y-intercept. And last but not least, the range of this function, well, I could see that it's going up, so then I'd say y is an element R since it's continuous, such that y has to be greater or equal to my optimal value, which was negative 27, right? That the y value of the vertex. All right, cool. So that is really the basics, the crux of quadratics, right? Those three forms, like everything comes from this, all the types of questions, right? Let's keep going here. All right. We got something here, which is how to identify if something is quadratic or not from a table of values or difference tables. So here we have calculate the first and second differences for the following table. I have a table of values with x and y. As you can see here, x is going up every time by 1. So it's like plus 1 every time. So x is increasing. What's happening to y? Well, the first difference, that's what this is. So I'll write it in pink here. First difference, I'll just shorten that, first diff, is going to be literally like, how do I get from 22 to 12? I subtract, so that gap right there is what's going to go there. I subtract 10, so minus 10. And then from here to here, I subtract 6, right? I hope you could see that. Subtract 6. And then from here to here, I subtract 2. From here to here, I add 2. So suddenly my sign changes from subtracting to adding. And then from here to here, I am adding 6. Okay? 6 to 12. There you go. So that's the first differences. Now, looking at this question, is this relation linear? No, it's not linear, because we would have known from like grade 10 that for it to be linear, the first difference has to be constant. So no, because the first differences, right, multiples, plural, first differences are not constant. Right? If they were the same, this would be linear. So if the first is not constant, let me find the second differences. Second diff. Right? So the second difference is from here to here. Maybe I'll just write it here this time. That's, again, actually, no, I'll keep writing it there. So from there to there, the second difference is, so here, negative 10 to negative 6 is a positive 4. The increase. Negative 6 to negative 2 is a positive 4. Negative 2 to positive 2 is a positive 4. Positive 2 to positive 6 is also a positive 4. So every time, it looks like the second differences are just equal to positive 4. So is the relation quadratic? Yes. It's quadratic because the second, that's my short form for second, differences, diffs, I'll just write diffs for short, are constant. Right? This implies that the degree, it's a good word, therefore degree is 2. So degree is a fancy word for just saying, a fancy term for just saying what is like for my exponent, right? So this is going to be like an x squared polynomial. That's the degree is 2, meaning that there's going to be the largest exponent for like any term. The largest, like sum of the exponent or product of it. The largest exponent is going to be a 2, essentially. Okay, it's long story short. If it was if the first differences were constant, well, then it would be linear, and that would be degree 1. So that's what linear means, okay? But this is not linear. Okay, what is the direction of opening and why? Well, if I'm just given a table of values and it's just first differences and second differences, well, you just kind of just say, well, not to say, but if the second differences are positive as opposed to negative, if it's positive, then it's going to be opening up. So the answer to this is it is like since second diff is positive, that means that it opens up. Okay, but you can also see this just from looking at this kind of, right? As x increases, so as I'm going from left to right in my on my function, I could see that, well, y is decreasing, right? From 22, it's going down to 12 to 6 to 4, and then it gets to 4, and then it's going up again it's going up like that. So as you can see, like it's a smiley face, it's a opening up parabola, so it's positive. Okay, that's it. Nice. All right, so that's difference tables. Now we get to some examples, which is just applying this, right? These are really nice and quick. So starting here, I have a parabola, a quadratic. For the given quadratic, state the vertex. That's this point right here. So it's going to be 2, 8. Nice and easy. State the zeros. That's going to be here and here. So the zeros are like my x-intercept, so it'd be -2, 0, and 6, 0. All right. Direction of opening, well, it's down, right? Because it's open. It's a frowny face. It's going down like that. So down. State the maximum minimum value. So I'm going to circle. Is it maximum or minimum? Well, clearly it's maximum because there's no value that exceeds 8. Like that value is a maximum. And the value of that maximum is 8. So it's just 8. State the axis symmetry. That is this line down the middle. The equation of that line is going to be x equals 2. In other words, it's the x value of my vertex. The optimal value is the y value of my vertex, as we got here and here. Okay, state the domain and range. Well, for any quadratic, right, regular quadratic, the domain is going to be element of real numbers. That's it. There's no such that. It just goes to the left and right forever. That's the domain. And then, so maybe I'll just write it like this. So it's because I'm writing it in line here. So I'll just write D for domain and R for range is equal to y is elements of the real number, such that y has to, since the vertex is a maximum here, I'm going to say that y has to be less than or equal to 8. That's it. That's my domain and range right there. Okay. By the way, axis symmetry, you can abbreviate that as AOS. It's okay to write that from going on. Find an algebraic model, then express it in standard form. Very interesting. So it wants me to find the equation for this quadratic function, right? So there's 2 ways to go about this. I'll show you the algebraic way first, and then I'll show you the more intuitive way as well. That works for generally nice quadratics like this. But the algebraic model, well, this one, I would go ahead and you could either pick vertex form or factored form. Let's just go with factored form here. So I'll go like y is equal to a, x minus r, x minus s. You can fill in what you know, and then there should just be one thing that you're trying to find. So I don't know what a is. I don't know what that vertical stretch factor is. So I'm going to leave it blank. I'm going to solve for that, and then I found the equation. But I do know that my zeros are -2 and 6. So when I plug them here, I gotta plug them in the opposite way because it's going to be -2, right? That's what that would be. Let me just write it that way in the beginning so you're seeing it. But yeah, this would be x minus 6. So I just plugged in for r and s there from here. So this was r and s. And now let me simplify that. So x is equal to a, right? I'm trying to figure out what a is. But this is just x plus 2, x minus 6. So you can go directly to there, okay? You don't need to show this step, but I'm just showing you why the signs are flipped there, okay? All right, now when I want to find a, what I do is I just pick a point that I know. So let me pick like a point on the actual function, right? So the best point here would probably be the vertex. So 2 and 8. So I'm going to plug in. So I have my vertex, so I'll just say plug in x comma y equals 2 comma 8, right? And if I do that, I'm going to get something like this. The y value is 8, so 8 is equal to a, and then I have 2 plus 2, and then again I have 2 minus 6. All right, so let's simplify this stuff right here and this stuff right here. So it's going to be 8 is equal to a times 4 times negative 4. Okay, so if I move over to here, 8 is equal to a, that's negative 16. And I'm going to divide both sides by negative 16, right? And so that disappears. And I get a reduced, it's just going to be negative 1/2. All right, so I can write my equation, algebraic equation in factored form. So I can, quadratic equation in factored form is just going to be y equals negative 1/2 x plus 2 x minus 6. So that would be my full equation right there in factored form. Express it in standard form. All right, well, I'm just going to have to use FOIL and expand this, right? Like this and like this. Let's just go ahead and do that as well. And then after, expand it by the a value. So y is equal to, I'll just do this in a different color actually. So y is equal to negative 1/2. If x times x is x squared, x times negative 6 is negative 6x, x times 2 times x is positive 2x, 2 times negative 6, 2 times negative 6 is negative 12, and let me simplify that. So that's going to be negative 1/2. X squared minus 4x minus 12. Just going to work over here. Now let's expand this into each term. So I will get y is equal to negative 1/2 x squared. Negative 4 times negative half is a positive 2, actually. So positive 2x. Negative times a negative is a positive, and then half of 12 is 6. So that is my same quadratic function from factored form, now in standard form right there. So pretty cool. That is the full way to do that. Okay. All right. So we have covered that example. Let's keep going here. Just a few more. This is again something that you would try, but let's just go over it like a word problem, a real life word problem here, and then I'll tell you the homework for this lesson. Okay, so this is something that you want to try. It's a real life problem application of quadratics. So the path of a firework is described by this function right here. Okay, so motion problem, where h of t is the height of the firework. So this is like the height in meters. Okay. And t is the time in seconds since the launch. So t is t equals 0 is the initial time. And then it goes on after that, right? Since the launch. Okay. Sketch the pathway of the firework. Is it launched from the ground or a platform? Determine the height at time 0 to find out, right? So some cool things here is, first thing we want to ask ourselves is, what format is this function in? It's a quadratic, clearly, because there's a squared here. But is it standard, factored, or vertex? Well, this right here looks very much like vertex form. So if I wanted to draw a sketch here, I'd start with the vertex, right? Vertex is equal to h comma k, which you don't have to write h comma k every time, but I just want to remind you. So that's 5 comma 124. Remember why it's not negative 5? It's because this is t minus h, right? So then h is equal to 5. Okay, so cool. So now I can just pinpoint, again, a sketch is going to be very much like this. So 5 and 124, not drawn to scale here, but let's just say that's, that vertex right here. And since the a value is negative here, negative 4.9, it's going to be coming down like this. Right? It's going to be coming down like this and like this. Now, for real life's sake, like if I kept going here, it would go into the negative time, right? By the way, this is time and this is h of t height. Those are my axes, right? But that would be going backwards in time. So what this means, like we don't really consider negative time. What this means is that my height is above the ground. So I have something where it's like it's starting at a height, it's starting at a platform. But again, let's verify this. I would plug in. So this would be h when time is 0, right? Because here time is 0. So let's figure this out, right? So this would be the sketch of my rocket. But let's figure out if the rocket is launched from the ground or a platform, or if it starts at 0. Let's do that. So h of 0 is equal to negative 4.9, 0 minus 5 squared plus 124. All right, so this is going to be negative 4.9 times negative 5 squared plus 124. And so this would be negative 4.9. We could see clearly that this is not going to equal 0. I'm pretty sure it's not. Maybe it will, but if it was, then it would start at the ground level. But yeah, negative 5 squared is 25, and then plus 124. So this would be, so negative, so I'm just typing this in my calculator, negative 4.9 times 25 is, oh, very close to 124. It's negative 122.5. Okay, so that's what that equals, plus 124. And then this would equal 1.5. All right, so we just found out that the rocket is actually starting at 1.5 meters. 1.5 meters, I don't need to include the units there, but yeah, 1.5 meters above ground at time equals 0, right? That's the initial value, right? Y equals 0, or h of t equals 0. I'm figuring out what the y-intercept is. I'm solving for t. Sorry, I should rephrase that. T equals 0. I'm figuring out what h of t is. That gives me y-intercept. Yes. Okay. If I set y equals 0 and solve for t, I'd be finding the x-intercept. That's something different. But yes, we did find the initial value there. Good. So moving on here, determine the maximum height of the firework. Well, we could see clearly that it is just 124 meters. 124 meters. It's the y value of my vertex. How many seconds does it take for the firework to reach the maximum height? It is the axis of symmetry, the x value of the vertex. It takes 5 seconds. Okay, 5 seconds to reach that maximum height. Determine the height 3.5 seconds after the firework was launched. So t is equal to 3.5. And I'm now just solving for h of 3.5. So back to my equation here. Negative 4.9. For t now, I'm subbing in 3.5. Use brackets, or just since it's positive, you could leave it like that. That's okay. But yeah, negative 5 squared plus 124. You could just do this in your calculator in one step, but I'll just simplify it here. 3.5. So let me do this just to make sure I don't make any mistakes. 3.5 minus 5. Yes, negative 1.5 squared plus 124. I'm just going to type this in once in my calculator here just to avoid any, I don't want it. This part is redundant. But yeah, negative 1.5 squared and then plus 124. So 1 second here. Sorry, it looks like just doing this on the computer here. It's not allowing me to, oh, I need to do time specifically. Is that right? Oh yeah, okay. So negative 4.9 times negative 1.5 squared plus 124. It's giving me an answer of 112.975. You could round this to the nearest meter. So you could say height is approximately 113 meters. That's okay. Round it up to the nearest meter. It didn't really state, so that's fine. Okay, cool. So it's at 113 meters in 3.5 seconds. Makes sense. And always you want to do like a quick gut check, right? If this height that we found somehow we made a mistake, if it was a value higher than 124, like 150, we would have made a mistake, right? So those are quick checks. How many seconds does it take for the firework to reach a height of 100 meters? Okay, so how many seconds does it take for the rocket to reach that height, right? So now I'm setting my h of t equal to 100. Okay, interesting. So now I'm saying, well, this is h of t is equal to 100. So I'm setting the answer to 100, trying to solve for time. So let's do this. And we have vertex form here. So I'm going to say 100 is equal to negative 4.9 t minus 5 squared plus 124. So I have to use SAMDEB, right, to solve for t, slowly unwrapping this. So I'm going to subtract 124 from both sides. I want to get rid of this 124 on the right side, trying to isolate for t on that side. So I'm going to get 100 minus 124 is a negative 24 is equal to negative 4.9 t minus 5 squared. Then I'm going to divide both sides by negative 4.9 to get rid of that on the right side. So on the right side, I should get negative t minus 5 squared. On the right side, negative 24 divided by negative 4.9 is going to be a decimal number. So I think what I'm going to do is, for now, I'm going to leave this as a fraction, 24 over 4.9. I'll leave it like that in fraction form. That's okay, and it's positive because negative divided by negative. But then I'm going to square root both sides. Okay, square root both sides. And so I will get t minus 5. And notice here, when I do square root, I'm going to get two answers, which is interesting, which is true, because there are going to be most likely, well, there are going to be two times. So 100 could probably be like over here, maybe somewhere. I don't know. There are going to be two times when the rocket reaches a height of 100, here and here. So I'm figuring out both of them, right? So I'll do plus minus. I want to make sure to do that. T minus 5 is equal to plus minus square root of 24 over 4.9. You could do this as a decimal, but I'm just keeping it exact now. And so now I get two answers, right? Like we said, one of the answers is t is equal to 5. So I add 5 to both sides. So I get 5 plus square root of 24 over 4.9. And the second answer that we get is t is equal to 5 minus square root of 24 over 4.9. Okay, so now if I grab my calculator here and type this in, I'm just going to do this on the calculator instead of the phone, so or instead of the computer. So 5 plus square root 24 divided by 4.9, I get an answer of 7.2 seconds. So for time, maybe leave it to one decimal place, because it's like, that way it's two significant figures right there. So I get more figures, so it's good. So I get 7.2 seconds is one answer, and the other one is 5 minus that, and I get 2 approximately, roughly, right? I'll put the dot there to say approximately, or the squiggly line, that's okay. But yeah, approximately 2.8 seconds. So two answers, which correspond to this time right here, that's about 2.8 seconds. And then this time right here, which corresponds to 7.2 seconds. Okay, so very interesting real life application of that. And then last question here is, how long is the firework in the air? Well, I'm trying to figure out, this is like the x-intercepts, x-ints, or like we also call this the zeros or the roots. These are all used interchangeably, really. But yeah, this means like, y is equal to 0. So I'm trying to figure out what is the t value, solve for t when y is 0. So I'm going to set h of t equal to 0 and then solve for t. So back to my function here, it's going to look like this. So it'll be 0 is equal to negative 4.9 t minus 5 squared plus 124. I'll subtract 124 from both sides, so I get negative 124 is equal to negative 4.9 t minus 5 squared. And I divide both sides by negative 4.9, so 124 divided by 4.9. So again, it's going to be a decimal, so I'll just leave it as a fraction. 124 over 4.9. I like to keep things exact until the very final step, just to avoid rounding errors and stuff. But yeah, this would be t minus 5 squared. Now square root both sides. And since I'm introducing the square root, I'm going to add the plus minus there. So I'm going to get t And I'll put this in front now. It's like, actually, no, I'll leave it like that. T minus 5 is equal to plus minus square root 124 over 4.9. And so I get two answers now, right? T is equal to 5, because I add 5 to both sides, 5 plus square root of 124 over 4.9, the whole thing square rooted, or I get T equals to 5 minus square root of 124 divided by 4.9, right? So two answers. Let's figure what this like, right? Approximately, I'll put the dot on top to say it's approximate. Here as well, I should have put the dot as well before. Yes, I did. Okay, good. So yeah, so approximately, by the way, this and this in math mean the same thing. So this is like approximate. I use this for approximate. Either one's fine. So yeah, so approximately equal to, let's figure this out. So 1 plus square root of 124 divided by 4.9 is going to be 10.0, roughly equal to 10.0 seconds, right? We're solving for time here. So time, that's one answer right there. That is the answer, because if I do this here with the other one with the negative, with the minus version, 5 minus, I'm going to get negative 0.03 seconds. That does not make any sense because I can't have negative time. So what we say here is, instead of putting a box around that, I'm going to say cross that solution and say not applicable, because negative time would mean like if I'm backtracking to when the rocket would have started. But mathematically that makes sense, but realistically there is no such thing as negative time, right? The rocket literally started at time 0 and it was starting at a platform 1.5 meters above ground. So my final answer would just be, when does it hit the ground? So when it goes through this motion right here, that time would be 10 seconds, roughly 10s. Okay, so there we go. That is the full solution to everything. This right here is the homework that I would like you to do for this lesson. So it's from, today's homework is from, so let me just paste this. Yes. So it's coming directly from the Nelson Functions 11 textbook. Try these questions out and you will be in good hands. All right. Thank you and have a great day.